questions from 5.1. I'm still getting over a bit of illness from the holidays, so apologize if I sound a little stuffed up. Okay, so this is probably going to go pretty quickly, especially the definitions. I'm just going to actually write the definitions out. Maybe I'll talk my way through them a little bit. Oxidation, well, to remember that, I like to think, well, Leo says Ger. And we need to remember what these letters stand for. Leo is losing electrons is oxidation. And Ger stands for gaining electrons is reduction. All right. So if I want to describe what oxidation is, well, oxidation is simply the loss of electrons, losing electrons. The loss of electrons. Simple. And reduction is the opposite, it's the gain of electrons. And if you don't like to write electrons, you can just write little e with a little negative sign there. That's a acceptable shorthand. All right. Oxidizing agent. This is where things get a little tricky. Very generally, an oxidizing agent is a substance that causes something else to be oxidized. And what's key here is that the oxidizing agent itself doesn't become oxidized, it becomes reduced. And that's where it gets a little tricky there. Okay. A reducing agent is the opposite. It's a substance that causes something else to be reduced. Looks like I ran out of space there, so a substance that causes something else, not itself, to be reduced. And it's worth mentioning that the reducing agent becomes oxidized in this process. Okay, and a redox reaction is simply an exchange or transfer of electrons between species. So, maybe I could generalize that. It says any reaction containing an exchange of electrons between two species. And if you want to get into it, very generally, that is really the definition of chemistry. Chemistry is all really concerned with just the exchange of electrons. That's what a chemical reaction is, when electrons get transferred or manipulated within a substance. That's really all chemistry is. And not even all electrons, just the valence ones. So this really is just another way of thinking about what chemistry really is at its heart. And that's actually one of the reasons I really love electrochemistry. It's because it just gives us this wonderful lens for thinking about what governs these forces that we're observing when we mix two things together in a beaker. All right. So the next two questions are pretty straightforward. So we're just going to label which of these substances, like what's happening to each of them. Let's see if I have a blue pen. I do have a blue pen. Okay. So in order to determine what's happening here, I have to just say, okay, well, I'm going to compare a species with itself on the other side. Like, what happened to zinc 2 plus to become just regular neutral zinc? Well, you started with a positive 2 charge and became neutral, so it must have got some negative charge to balance it out in the form of an electron. And so zinc 2 plus must have, that green pen comes in a little heavy. This is a 2 electrons are transferred to zinc. Okay, so that means there's a gain of electrons. Gain of electrons. That means a reduction. That means this process is a reduction. Okay. So let's take a look, see if we can use that information and say, well, since we know that zinc is getting reduced, maybe we can say, oh, okay, that means the reduced species, the species undergoing reduction, is zinc 2 plus. It doesn't mean the reducing agent is zinc 2 plus, because remember, the reducing agent causes something else to be reduced. So we'll come back to the reducing agent. Let's take a look at the magnesium, turning to a magnesium 2 plus ion. All right, so what's happening there? Well, it starts out neutral, and then it becomes a positive 2 charge. That means going from here to here, we're getting a subtraction of 2 electrons. It's losing charge. That's why it has a positive charge, losing negative charge. That's why it gets a positive charge left over. There's more protons than there are electrons. Okay. So that means we have a loss of electrons going from magnesium to the magnesium ion. And a loss of electrons is an oxidation. So the species that got oxidized is magnesium. Okay, now let's go back to reducing agent. Now we know that zinc got reduced. So what is the substance that caused zinc to become reduced? It was the magnesium. It was the other substance there. So the reducing agent is magnesium. And through similar logic, the zinc 2 plus is the oxidizing agent. So what species underwent reduction? That's the same thing as saying the reduced species, really. It's just another way of saying it. And a species that undergoes oxidation, experiences oxidation, is the magnesium solid ion. Pardon me, solid atom. The species that loses electrons, the species that loses electrons is the one that is getting oxidized, which is the magnesium in this case. So the magnesium is losing electrons. Species gaining electrons, okay, that's zinc, zinc 2 plus. All right, so the reduction is the zinc zinc ion turning to a zinc atom. And to do that, it must gain 2 electrons. So that means that the electrons are a reactant. They're going to be combined with zinc to form solid zinc. Actually, you know what? We're not worrying about phases, so I'm going to ignore that for now. Just neutral zinc. We'll just focus on the neutrality of it. Okay. And the oxidation, the loss of electrons, is where we start with a magnesium, neutral magnesium atoms, and it splits into some electron, or let's start with the magnesium ion. And in addition, it must have given off these 2 electrons. And that's it. All right. So I think I'm going to go through example 3 really quickly because it's really the same thing as example 2 for the most part. If I take time at all, it'll be on these first steps about deciding where the electrons are traveling. But beyond that, I'm going to kind of rush through this a little bit. The logic is going to be pretty much exactly the same. All right, so I'm going to choose a species. And let's look at the fluorine. Okay, I can see that we have this F2 fluorine gas, and it's neutral. There are 2 of them, but they're neutral. They're the same species. So that means that they must have started with a charge of 0, and then they get this negative charge. It looks like fluorine just did what fluorine does best. Fluorine is notorious for stealing electrons from things. It is the most electronegative, most electron-thirsty substance. Or pardon me, not substance, but element. And so it looks like there's a gain of electrons, a gain of negativity. All right. And then we'll look at the tin. That goes from Sn2 plus to Sn4 plus. So it looks like the charge here became more positive. You get more positive in terms of electrons when you lose electrons. Because electrons have negative charge. So you lose or shed some. It's a loss of 2 electrons. And I guess it's a gain of 2 electrons to make these 2 guys. So, I mean, it's 1 per fluorine, but it's 2 in total. So we'll just have some nice balance there. All right. So with that in mind, I'm going to kind of rush through this a little bit quickly. All right. Reducing agent is the one that got reduced, gained electrons. So that's F2. No. Haha, that's the reduced species. Oxidized species is tin. That means the reducing agent is also tin. And the oxidizing agent is F2. Species that gets reduced or undergoes is F2. F2 plus. Species losing electrons is the tin. Gaining electrons is the fluorine. The half reaction, okay. So we've got this. Let's do that. Fluorine first. So we start with F2, and that's a gas. And you add 2 electrons to make this product, which is these 2 F minuses, fluoride ions. All right. And this reaction is so violent that it's one of the good reasons you're not supposed to eat your toothpaste. All right, now, oxidation half reaction. Okay, so oxidation, the loss of electrons. So we got this tin. I almost said selenium, which is Se. Anyway, so makes this different valence tin, and these 2 electrons. And that's it. Okay. Let me know if you have any questions about that.